Hi everyone, I'm James from Gypsylab in Grenoble, France, and my workshop today is going to concern mass interaction physical modeling within Faust. So what is mass interaction in physics? Basically, when you're looking at solving a physical system in classical point-based mechanics, like you might have done in high school, for instance, you describe a physical system as being composed of a number of simpler entities that are coupled together through some interactions of some sort. So you might have a punctual mass here, another one here, maybe something over here. You could have a spring that couples two masses together through Hooke's law. You might have some gravitational pull or any other kind of interaction force. And all these things together will give you a system of partial differential equations, and if you take all that and you solve it, you can obtain what you're looking for, such as the motion over time of one mass in the system, for instance. And that's exactly what we're going to be doing with our system. So if we look at how this compares to other types of physical modeling, in modal synthesis, for instance, what you would do is mathematically describe all the vibration modes of a generally linear physical structure. So you'd basically say you have a string or a plate or something, you'd figure out all the vibration modes for this real mathematical object. And once you have that, you can basically just resynthesize all the vibration modes through additive synthesis, and then obtain something that basically behaves in the same way as the physical object would. Whereas in waveguide modeling, for instance, you'd approach things differently by representing motion as traveling waves, basically two traveling waves in opposite directions that represent basically motion within a given medium, and then you'd add scattering junctions and things like that to account for places in your system where some waves might be reflected back or transmitted forward, and so forth. And finally, in finite difference schemes, what you do is take a certain physical system as a point of reference, say a string or a mesh or something like that. You'd describe the continuous system for this physical entity. So for a string, you'd use the one-dimensional wave equation. For the mesh, you'd use the 2D wave equation, and so forth. You'd define some boundary conditions for this system. So where is the wave going to bounce back on borders and things like that. And once you've completely described this system as a continuous physics problem, basically, you'd look at ways to best discretize this system to solve it numerically. And what we're doing in mass interaction is kind of a step back from that, in that we discretize the basic physical elements upstream, if you will. So we're going to have a discrete time mass, a discrete time spring, and all sorts of other interactions and things like that. And then what we do when we have these things is we can just assemble them together to build physical networks, basically, and do what we want. It's interesting also to note that there are many equivalencies in basic cases such as strings or meshes and things like that. You can find mathematical equivalencies between a lot of these different approaches, and I'd refer you to Stefan Bilbao's book on numerical approaches to sound synthesis to have a deeper glance at that. Mass interaction modeling first came to be at Acroé in the 1970s, and mainly through a concept and a formalism called cordis anima, which defines the ground rules, if you will, for mass interaction physical systems. And that's given rise to software such as Genesis and MIMS, and along the years gave rise to many other people finding an interest in mass interaction modeling and developing their own ideas and their own tools. and that ranges from tau and cymatic to PMPD, which is physical modeling in pure data, all the way to HSP, haptic signal processing, and to Synthomodeler, which was designed by Edgar Bedal in Faust, and which is quite similar in many ways to what we're going to present in our work. So now I'll quickly cover what we at Gypsylab do in regards to mass interaction physical modeling. And for that, you can have a look at the MICreative website, micreative.eu. And here you can find all the work that we conduct regarding mass interaction physics, be it for Faust, for MaximSP, and for specific art science projects. And within this, we're going to start with the paper that we published at the Linux Audio Conference in 2019, entitled Formalizing Mass Interaction Physical Modeling in Faust. And what this paper gives is a kind of general framework of how the basics of mass interaction physics work and how we can implement them in Faust. So if we look at it here on the screen, the motion equation for a continuous time mass would be given by Newton's second law, quite simply, as F equals ma, F being the force applied to the mass, m its inertia, and a its acceleration. And so that naturally means that m equals second derivative of x over dt, so the second derivative of position over time. And if we want to find a way to basically give ourselves a kind of a state equation in discrete time for this system, what we can do is apply a second order central difference scheme to the variable x above. And what's that going to give us? It's basically going to end us up with this this state update scheme wherein x of n plus 1, so that the new position of a mass is going to be equal to 2 times x of n, its current position, minus xn minus 1, which is the previous position of the mass, so you have the velocity of the mass in there basically, plus Fn, which is the force applied to the mass in the latest time step, divided by m. And m here is the discrete time inertial parameter, and it's defined as the continuous time inertial value divided by the sampling interval squared. So that's something we kind of have to keep in mind. And if we go a little further and look at how a spring could be approached in discrete time, well, if we look at a linear spring that obeys Hooke's law, you'd have something that generates force which is equal to minus k, which is the stiffness value, times x2 minus x1, x2 and x1 being the positions of the masses connected by the spring. And since there is no kind of temporal or memory aspect to this interaction, it's just a continuous equivalence, basically, this can just be discretized immediately. So equation 6 here gives the discrete time version of this. And if we want to approach damping in a system like this, we'd actually express velocity as something using the backward Euler difference scheme. So basically velocity is going to be the current value minus the previous value of a position. And so we'd end up with something like in equation 11, where the force applied by a dampened spring would be one term which depends on the difference in positions between the modules it connects, and one term that depends on the difference in relative velocities between these connected masses. And of course, Newton's third law means that an interaction must apply its force symmetrically and with opposite signs to the elements that it attaches together. So the force that this spring is going to send to mass number 1 is going to be minus Fn, for instance, and the force that it's going to send to mass number 2 is going to be plus Fn. And that's basically all we're going to have to work with, is this system where we have masses that evolve over time depending on their state, so their position and previous position, and on input forces that they receive. So they're going to be objects that take a force as an input and output a new position. And on the other hand, interactions are things that will take in two input positions and velocities. So basically the data from two mass elements as an input, and that's going to produce a force that we can loop back into these mass elements. And that's basically all we're going to be working with. Is kind of really simple in a way. So now we have the equations for simple masses and springs and things like that. We can have a look at how we've implemented these and how they work within MI.lib, which is our Faust library. You can find the library in the standard Faust library. So on the Faust library's website, you have this MI section. And here you can have a look at different papers that cover mass interaction physics. And you have the documentation for the library. And what we're going to do is go straight in and have a look at our basic mass. So mi.mass. I'm not going to explain the parameters just yet, but just to show you how it's built within Faust. It's designed as a recursive body abstraction. And this is used with a letrec function within Faust, which allows us to basically write this equation 3 as is into Faust. So this mass element expects a force as an input and produces a position as an output, and inside it you have basically state variables for position and delayed position. If we now look at spring damper, for instance, mi.spring damper. Again, I'll just kind of set these to basic values for a start. Okay, so this is a basic linear spring damper. It takes two input values, which are the positions of the elements that it's going to couple together. One part of the system is going to calculate a difference in position between these position values and apply that, multiply it by a coefficient to give the stiffness term. And the other one, using a small memory system, is going to calculate the difference in relative velocities between these two inputs. And the output is going to be the force produced by the spring, and it's going to apply on one hand with a -1 multiplication to account for Newton's third law, and on the second outlet it's just going to pass straight through. So now that we have this, let's try and design our first very basic mass interaction system. So we'll start from the mass again. And so the first parameter, the first argument to the mi.mass function is the discrete time inertia, so this big M. The second is a gravity value. We can just leave that at 0 for now. And then you have the initial position, 0, and the initial delayed position, which infers velocity, which is also 0. It's important to specify here that all the masses in our systems are going to move along a single 1D axis. So we just define positions as scalar values here, which is different to, for instance, 3D mass interaction modeling that we might discuss in perspectives. So we have our mass here, and what we could do just to check if this guy works is set up an input function for it. We could use a button, call it test. Send that through ba.impulsify just to make sure we only send one impulse when the button is clicked, and we're going to give this a really tiny value here. So create this input, and we're going to just put it in as a force input for this mass. So there you have it in the diagram. If we run this, well, it all kind of happened fast here, but if you manage to see it on the output analyzer, we sent a force impulse to this mass, which isn't attached to anything, that isn't subject to any gravitational pull or anything, and it just basically flew up at constant velocity, which is what you'd expect from a simple physical system like this. If we send a slightly smaller force, it moves up slightly slower, which kind of makes sense. So this isn't really exploitable for anything, especially not sound synthesis. So let's start making something slightly more complex. One thing that I forgot to mention is that all of these examples that I'm going to be covering are placed in a GitHub repository that's going to be given with the workshop. So you can either code them at the same time as I do in real time, but you can also find all these examples with some cleaner comments and things like that on a GitHub repo that will attach to the workshop. And so now we're going to build a basic oscillator. And to do this, an oscillator is going to be a mass, a fixed point, and a spring damper between the two. Well, a damped harmonic oscillator will be. So we'll put an mi.ground. Sorry, my typing is horrible. Mi ground, and this only takes one input position, which is 0. We'll take away this input function for now. We don't really need it. So here we have two material elements in the system and nothing else. And one thing that you need to know with MI.lib and with this mass interaction thing is that in Faust we're going to define all our mass type elements as one parallel composition and all our interaction elements as another parallel composition that follows it. And then we're going to sort out basically routing functions to pass the right positions from the masses to the interactions and the right forces to feed back from the interactions into the masses. So if you just want to put one spring damper, for instance here, spring damper, blah blah blah, give stiffness value here, damping value, and the values here are actually the delayed position of the mass and of the ground module, and these are just needed so that the first step of computation for the spring damper computes correctly. So we can, well, don't have to pay too much attention to that right now, but it's quite important to keep in mind. And so there we have a system. So we have material elements going into an interaction, but then we just send the forces out and we don't do anything else. So we don't have a coupled physical system here. And that's what I'm going to do now. Just make this slightly cleaner looking. You're going to see a lot of routing errors and things like that in the first steps of me making these models. And that's just something that happens in Faust. Anyone who tells you that they can write seamless Faust code without generating cryptic errors is either Jan or a liar. So I have my cheat codes here, actually, just to make sure I kind of know where I'm going with these models. So while I was rambling on here, what I did is build this recursive loopback composition thing here. Can't remember the exact name in Faust terminology, but what it does basically is takes the forces that are output by the spring damper and loops them back to the masses. And that is, well, that's a good first step, because that means that we actually have this system which will start behaving like a harmonic oscillator. And if we want to check that, we can just set an initial value for the mass delayed position and report it into the spring damper here. And if we run this, it's kind of faint because I've given a small initial velocity, but we can actually see that something is moving and we can hear this tiny harmonic oscillator sound. So let's take these back off. Problem here is that we have this system, but we don't really know how to, we don't have much control over it. We don't really know how to input things into this kind of closed loop system. Don't really know, well, for now we're listening to the force produced by the spring, which is maybe not what we want. And so that's what we're going to do now, is build some stuff around this to make our life easier. And so the first thing that we're going to do is be able to add an input force to the system. And for this, I'm going to use the with system in Faust to write a routing function, root forces, and this is going to be placed just after the spring damper. So the spring damper produces two opposite and equal forces. We're going to call them FSP1 and FSP2. And what we're going to do quite simply is say that this routing function outputs two signals, but in the first one, which is the force that applies to the mass, we're going to say that is FSP1 plus input 1, and the other one stays FSP2. And this is going to be placed right here after the spring damper. Let's have a look at the diagram. So here we have it. We can bring this impulsify value up a bit now, probably. And if we run this, it's still very faint. I'll take it up to 0.5. I hope this isn't too loud. We'll see. Okay, so now we can actually input a force into the oscillator, which is nice. And however, we're still listening to the force generated by the spring damper, so that's not great. And to help us out with this, I'm going to write a root positions function, which is going to go after the masses, and it's going to take position of M1, which is our mass, and position of ground, which is the ground element. And what we're going to output from this is the positions that are needed by the spring damper, so PM1 and PG, and we're also going to add a third signal, which is PM1 again, and that's basically just adding a cable so that the position from this mass can run along through here and go to the output. So we'll set this up here just after the masses, and this is giving us some errors because we're adding, well, we basically have three signals now here running into the spring damper section, and we only have two inputs for the spring damper and for the root force function. So we're just going to add some pass-through signals here. Okay, so now see we have this system which duplicates the mass position as an output, and this runs along to the output here. And what we can do if we just want this position output and that we don't want the force outputs of our spring, which we might not be interested in, we can just discard the first two signals of this guy and add one pass through for the position. Okay, so we've cut these connections here, and if we have a look here, ooh, this is loud, take it down a bit. So we have a harmonic oscillator that we can send an input force to, and we're listening to the position of the oscillator, which is nice. And this is where things get slightly hairier, so bear with me, and we're going to do things the hard way first, and then we'll see how we can do them in a much easier way. So first we've added another mass up here. We've added another spring damper to the system, and obviously none of this compiles anymore because none of the routing is correct anymore. So first thing we're going to do is change the root position function here and add PM2, which is going to be the position of our mass number 2 that's going to be around here. And the two spring dampers that are going to be here are going to expect the positions of the masses that they connect as input. So that's the order in which we need to place things. So our second spring damper is going to act between mass 1 and mass 2, so PM1 and PM2. And we still keep PM1 as a pass-through signal for the output. So in a similar way, we're going to change the forces here, the force routing function. So we're going to do S2, well, FSP2 actually is kind of more correct. Well, no, actually, F2SP1 and F2SP2, because that's the two outputs from the spring. And so this kind of builds, but in a weird way now. But we need to think about what this root force function needs to be doing. and how this system acts. So the first spring damper connects the ground to the first mass, and the second one connects the first mass to the second mass. So the forces that need to be sent back to the first mass are the first outlet from the first spring damper, the input force that we added earlier, and the first outlet from the second spring damper. And we also need to add another force outlet, which is going to be the force acting upon the second mass in the system. So that's F2sp2. And so here we can see this horrible sequential composition error in Faust, and that's the stuff that you might have to deal with if you try writing these codes by hand. It kind of gets messy quite fast. And the problem here for this is that we've created a routing function that creates 3 output forces that need to be looped back into the masses, but we haven't changed the value 2 to 3 in here so that this actually works the way it should. So the force that's destined to the first mass is looped back here, then the second, and then the third. And this should build. I think it has built. And this happens sometimes. I just need to reload the page for the audio to come back. There we go. And if we actually listen to this in some more detail, this actually no longer is a simple harmonic oscillator, but it's a system that has 2 modes of vibration because we have 2 masses in the system. However, if I told you now that we were going to use the same principles that we had been using up to now and build a string of 20 masses or something that's not regular, you'd be looking at me like I'm crazy, because this is a pain. Doing this by hand in Faust is tricky because you have to do lots of mapping and things like that. And actually we have quite a nice solution for this, which is a tool called MIMS, which is a mass interaction model scripter. And we're going to go and find this guy. So if we go back to the MI Creative website, here we go. Go to something called tool MIMS. And we've built several prototype versions of this model scripter over the last couple of years, but the one we're going to use now, and probably the most stable one, is this MIMS Online, which is a JavaScript interface that allows to design physical model code, represent some features of the models, and then convert that automatically into either Faust code or Gen code for MaximSP. So the first thing we're going to do here, for instance, is build a mass, and there's a help section here that shows you what the different modules are and what the terminology for scripting them is. What we've done here is set up a first mass that's named M. It has an inertia of 1, and this here is the actual position of the mass on this bench. So we have one element here, and that's it. And we're going to redesign the system that we had before. So we're going to put a ground somewhere, place it somewhere different, just so there we go, so we can see both of them. Going to put a spring damper between these. So the way you do this is you declare the name for the spring damper, the type. Of course, you can look at this again in the help section. Then we define who's going to be connected by this guy. So M and G, and give it a stiffness and a damping value. And here we have this line here between the two. And now we're going to set up an input being a force input on M. And out 1 is going to be a position output also on M. Sorry, I forgot T here. There we go. So we have these kind of funky input-output representations here. They might change over time, but I mean they help us see what's going on at least. And the cool thing here is that this generates this Faust code automatically. which is nice. And so if we take this, bring it back into the Faust IDE, we're going to scale down this force input just a tad. There, so we've rebuilt the basic oscillator. And if we want to find the system that we had before, the two masses and fixed point system, we just set up a third mass here. So this compiles and we can see the third mass, but it's still not attached to anything. And I'm going to add a second spring damper between M and M2, same parameters for now. And there we have it. And we can take this guy, go back into the IDE, copy all of that. Sorry, that was loud. One thing that you have to do once you have the scripted model code generated is often scale your inputs and outputs a bit, just to make sure that the excitation you give to the model and what comes out of it is kind of on a normal scale and doesn't saturate the audio output. And that's basically it for our first model, and maybe we can start building some extra things now. The first thing I'm going to show you is how we can excite this model slightly differently than we had up till now. And we're going to do that first by removing this force input. And we're going to add a mass to the system. We're going to call this mass hammer. It's going to be a regular mass. We're going to make it a bit heavier than the others. And we're going to set a parameter that we're going to call gravity, and this is something that is important to know, is that you can say grav here is a parameter and has a certain value, so I'll put it as 0.5 for now. So that's the gravity that applies to our mass, and we're going to define its initial position here. So let's just put it at 1, 0, and 10. So we're going to place it above the other masses in the system, and we still need to give it an initial velocity. So there we go. Now we have this mass here, and we can see it. And what I'd like to do is basically throw this mass down onto this two mass system, and so I'm going to give it an initial speed of minus 100 units per second, and that's this last parameter here that you can find in the help file. And if I want an interaction between this and what's underneath it, I'm going to add another interaction, which is a contact type interaction. It's going to act on M2, for instance, and well, M2 is going to be collided into by the hammer. So there we go. These contact interactions take a stiffness term and a damping term. So let's just set it up like this for now. Now we can see this in the scripting window, and we have generated code for the model. Let's bring this back into the IDE, and I'm going to bring up the audio gain slightly so we can hear this better, but you might have heard it already. We have this kind of bouncing ball that bounces on this two-mass system. So now what we're going to do is design some strings and things like that using this mass interaction model scripter. So we're going to take all this down, and we actually have a script generator, which is quite practical, in which we can ask to define a string with a certain number of masses with a given name, initial parameters, so you can kind of look into all that and see what it does. And if we just slide this guy into here, we have a string of 30 masses. And so first things first, I'm just going to make sure that we can interact with this string. So I'm going to add a force input on, I don't know, mass number 10 of the string. You can see it appear here on the render, and we're going to get an output position, pos output, and that's going to be on the mass number, I don't know, 27. And he's not happy with that because I had a typo. So this again generates some Faust code, and you can see here that the routing functions would be extremely annoying to code by hand, and so we're kind of happy that this all is done for us. So here we have it. I'm just going to reduce the force input signal to make sure that this isn't too loud. How does it sound? Sounds nice, sounds low, so we can bring up the stiffness of the string here. Interesting thing when you generate with scripts is that it automatically creates these labeled parameters so that you can change these directly in Faust. So if we take this up to 0.3 maybe, there, and now we can, there. So this is kind of a reasonable sounding, very basic string made of 30 masses. So if I want to pluck this string, I'm going to take out the first force input, because we don't need that anymore. And I'm going to change this into a position input, and it's going to have an initial position of, let's say, 1, 1, 0. And what that does, if we look at the model view here, you can see a mass here that's been added to the system, and that's actually going to be controlled by an input signal in Faust. So it could be a slider, it can be audio, it can be basically anything that you want. And quite simply, we're going to add an interaction called an NL pluck. If you look into the help, you can see the parameters that it expects, and we can show you the force profile as well for the interaction. And this is going to act between the input 1 and between I don't know, mass 18 of the string. First parameter is the plucking stiffness. We're going to set this to 1. The plucking scale basically dictates where the tipping point for the plucking interaction is, so where the pluck kind of goes through the string and allows it to vibrate freely. And the last parameter is optional, but it's damping, and so that means that when you rest the pluck against the string, it's actually going to dampen the vibrations and not just kind of create this weird inharmonic tone. So I think this is okay. So let's go back into the IDE. We're here, and see we've changed this now. This input is now a position input, and it has a slider. And it works. We'll bring the audio up a tad. So here we're in contact with the string. We're pushing it up, and at one point we pluck it, so the pluck goes through the string. So quite simple, really. And let's say we want to make things slightly more complex. Let's add a second position input. Put this one at 2, 1, 0. The only position that really matters here is the Z, because that's the initial height of the pluck. All the rest is just for the model rendering, so it's just for us to kind of see where things are and how they're working together. And we're going to put C, a contact between a certain point of the string, strm. We have a 30 mass string, so I'm going to go ahead and put on the damper on 20, so we can maybe excite a natural harmonic. And so a contact interaction between that part of the string and the input, and we're going to make it quite soft in terms of stiffness and quite damped. And what that means, you can see it here, is that we're going to add this damper, so we can come and press down onto the string and change its vibrating properties, because we're basically applying pressure onto it. So if everything goes well, now we have 2 inputs and outputs. Actually, one thing that might be nice to look at is what the model looks like for something like this. So you can see we have all the array of these masses, which are actually oscillators in this case, the fixed points, the position inputs, the master link routing, all the interactions, and the routing here, and it kind of all goes back. So that's kind of simple enough for a 30 mass string, but it becomes absolute horrible stuff when you have bigger models. So now we have 2 position inputs. I'll just up the output gain a tad. Okay, this is okay. And if we bring this guy down, we can actually, we're just pressing lightly on the string, and we can bring out some natural harmonics. This the mass isn't positioned exactly on a vibration node of the string, so we're actually kind of damping it quite a bit, but it still works. And now, finally, let's see if we can bow the string instead of plucking it. So we're going to use exactly the same system as we had before, but we're going to change this NL pluck interaction to an NL bow. NLB we're going to call it, still between the first input and an element of the string. And the parameters for bowing, you can find them in the help here, are the nonlinear friction and a scaling parameter as well, and you can decide if you want a smooth function or a linear function, or a piecewise linear function for the bowing interaction with the last term. So what I'm going to do to make things easier is I'm going to create parameters for the nonlinear friction value and the nonlinear scale value. So I kind of know in advance which parameters I need here in terms of values, but you often need to explore a bit to get the right values that give adequate friction for a given system. So the things kind of look the same now, except if we go into here, we can see that we have an NL bow here in the system, and we have some additional parameters for the friction. So let's bring that back into the IDE. It's going to look more or less the same as it did before. And now what we want to do, well, we can see if this actually does anything yet. It does, but it's very, very low, and that is because I'm going to have to scale some of my data here. The bow position, which is the first input, is going to have to move in a lot broader ranges for this to actually generate enough friction. So with this set of parameters, if I give it a course between minus 300 and 300, that's a decent value. So this works, but it's pretty ugly, and the reason for that is actually quite simple, is that bowing input signals need to be very, very smooth in order to perform well with, well, basically these velocity driven friction algorithms are very sensitive to noise in the input value. So I've just set a bunch of smooths sequentially after each other here in the position. And there we go. And we still have the finger to generate harmonics. So we can slightly change the way the bow sounds it if we press down on there. And of course, what we can do is create a new slider here. So the NLZ actually corresponds to bow pressure. And we're going to set this guy initial value at 0.3, going from 0 to 1 with a scale of 0.001. And so now we still have the bow, and we can lighten the pressure. So nice and smooth bowing. Or we can up it like crazy and start getting some nice screechy sounds. And finally, what I'm going to show you now is how we can make stuff like this sound a bit better, and that basically pertains to the complexity of the vibrating structure. We had a very basic 30 mass string here, and 30 masses, in all honesty, isn't enough for a discretized mass interaction string to sound kind of very convincing and real in many cases. So I'm just going to go ahead and set a string with 200 masses. I'm going to bring this in here, so the script is getting a bit longer, but it doesn't really matter. And if we look at the model view, still looks the same, but it's kind of more compacted. And now what we might want to do is just change these contact positions slightly. So this guy is gonna dampen the string at half the length at 100. The bowing position is okay, we'll keep it there, and we'll set the output position slightly closer to the edge actually, so on the 10th mass. Note that you can also use several position outputs to have stereo or as many channels as you want. That's not something that we've done, but you can. And so we're going to take this guy, go back into Faust. I'd like to keep my position scaling for the bow, so I'm going to take all this stuff here and delete it. And probably have some duplicated stuff here that I need to take off, but there, so we've kept the bow, and I'm just going to, just going to put the bow pressure function back in here. So 0.3 from 0 to 1 by steps of 0.1, that should be okay. So same object, but and what's happened here? We probably need to lower the output gain for us. Oh no, I know the problem. We've made this string very floppy. I forgot to set the initial stiffness, so it's super floppy, and that's why it was all over the place. So if this is better, and if we bring this there, and if we're good enough, we can get some kind of decent Helmholtz motion going. So these triangular waves you see on the output, and if we press down on this harmonic point, we'll tend to bring out the first harmonic of the string. So now that we've done some basic strings and things like that with MIMS, I'm going to show you a slightly more complex model that I designed earlier. And this model contains several triangular structures that we're going to be able to hit with mallets, basically. So I'm just going to slide this MDL file into the editor and press Ctrl Enter to make sure it recompiles the view. And here you can see what the model looks like. So three triangular structures that have fixed points on the extremities, and you can see the code generated here for each of them. And at the top of the model we have all the kind of coupling and interaction elements for this model. First of all, we have a common bridge which is placed here, and that's a big large mass which is going to act as a kind of coupling point for the sound. So we're going to connect each of the triangle structures to this bridge, following these spring connections here. And then we also have hammers. We have three of them up here that you can see probably in the interface. And these are simple oscillators that are resting above these triangle structures, and we're going to be able to send force impulses to these hammers so that they come down, hit the triangles, and come back up. And the damping of the oscillator is placed near critical damping so that you don't get multiple rebounds and things like that. And finally, the last thing that we have is some small non-linear spring dampers here, which are placed between the different triangle structures. And what that does is just adds some more sympathetic resonances between the structures, and the non-linearities in these spring dampers bring out some interesting sound aspects. So let's go ahead and grab the Faust code for this, go back into the IDE. It's quite a big model, so it'll probably take a few seconds for it to compile. Let's see. Yes. Okay, we're not too bad. And what I want to do now is just to condition my my input signals and things like that properly, so that things work the way we'd want them to. First of all, the force impulses that I'm sending to the hammers need to be directed downwards, and I'd like to be able to determine the amount of force that I send to them. So I'm going to add another slider that's going to be called intensity, and that's going to go from 0 to, well, it's going to start at 1 and go from 0 to, I don't know, 4 by steps 0.01. And this is going to be common for all of my hammer inputs. So I'm just going to put this here and here. So this is going to control for all of them. If I start using them here, we can't hear anything because the this huge bridge that I connected between all these triangles only basically its impedance is so massive, its mechanical impedance, that its motion is very small. So I'm going to multiply the output gain by 100, and I could actually push it probably even to 1,000 to okay, so here we're starting to get somewhere. I'll bring it up slightly more still. And what I'm going to do is add some controls for the stiffness of each of the triangles. So call this one triangle 1 stiff, go it, yeah, from 0.001 to 0.3 by steps 0.01, and I'm just going to copy this and duplicate the control for the other triangles, and then we'll see how this model actually sounds. So there we go, we have everything here. If we start using the hammers, we have quite a moderate attack here, and if we bring the intensity up, slight saturation on the audio here, that's I should bring the gain down maybe a bit. I'm going to up the damping slightly because the resonances are very long here. And if we start detuning these triangles from each other, we can get some interesting sonic results. So this is kind of moderate attack levels, and if, on the other hand, we bring the intensity down to something really small, we get this nice, very soft attack. Now I'd like to discuss some perspectives and also some limitations to the work that we've done regarding MI.lib. And the first of these concerns optimization of the actual simulation code. Despite the system allowing to easily model fairly complex systems and such, we still see quite an important gap in performance from automatically generated Faust C++ code to manually handwritten and hand-optimized C or C++. We're yet to conduct extensive benchmarks on this, but the performance gain of writing straight C or C++ code for a given model can be anything from 3 to even 10 or maybe 20 if you start using manual vectorization schemes and things like that. The second aspect that we haven't implemented yet in our library is the use of macro physical elements in the same way you do in finite difference schemes. Each physical construction that we build in mi.lib so far is built by assembling single masses and interactions together, often in quite regular and homogeneous patterns. And if we actually create macro elements like a string, a mesh, a triangle, or anything like that, on the one hand we can optimize the formulation of these elements to speed up the calculation, and on the other hand it opens up possibilities for interpolation in connection points or coupling points to these structures, for instance, which is something that we cannot do as of yet with the core of our library. There is one example code in which I've prototyped some of this that I'll join in the GitHub repo, so you can have a look at what we can do to build kind of wrappers around these macro objects like strings, but there's still a fair bit of work for us to be able to integrate that fully into the library. And finally, something that we still need to do quite some research upon is to see how we could incorporate 3 degree of freedom physical models into MI Faust. As of yet, all our models work with 1 degree of freedom for each of the masses, so the masses all move according to a single axis, despite the fact that we can display them on a 3D rendering view. And if we go down the 3 degree of freedom road, I think there's a lot to be gained in terms notably of strongly non-linear behavior in the acoustical structures that we can build. So I hope you have fun with these tools and that you can use them in your own practice to build physical models and basically just create interesting sounds. Development on these is very much ongoing, so everything I've shown you here will be evolving over the next few days, weeks, months. And to evolve in the right direction, it's important for us to to get feedback also on things that work and things that may not work. So feel free to hit us up with bug reports on GitHub and things like that. I hope you enjoyed the presentation and happy modeling.